In this video, we'll be looking at the list data structure and considering the differences between arrays and linked lists. A data structure, such as a stack, like a stack of books piled on top of one another. A queue, just like a queue of cars waiting behind each other in traffic. A tree, just like a family tree with all the different hierarchies. Or a linked list is a way of holding and organizing information. Examples of lists in real life might include a shopping list, your contact list in your phone, a list of Facebook friends, or a list of 5,000 students enrolled in a college. One of the common questions asked by programmers is, when would you use an array versus when would you use a linked list? To answer this, we need to understand three basic things. 1. How a list data structure functions. 2. Its processing speed. And 3. How well it uses memory. Let's start by looking at how arrays work. Due to their fixed size and specific indexing of the array elements next to each other in memory, the anticipated size of the array needs to be specified and fixed well in advance. At runtime, the size of an array can no longer change. But more importantly, any insertions into the array, or indeed deletions from the array, requires quite a bit of shifting of elements, which uses up a lot of processing power. If the number of elements used in the array decreases, there will be memory allocated to that array which will not be used. If the number of elements in the array increases, there won't be enough room to fit them all into the allocated space. So, back to our shopping list. If you wanted to remove the T item from the list, and this was an array, you'd need to shift everything backwards. This is quite a time-consuming and costly process. If you wanted to add another item into the middle of the list, you would need to squeeze it in. And with an array, this would require quite a lot of shifting. However, with a linked list, it's a very simple process. Another advantage is that the size may change at runtime. An array size is fixed and cannot be changed. For very small data sets, when a fixed size doesn't really make a difference, and that won't involve any shifting around of values, arrays are a pretty good structure to use. They also have the added advantage of indexing, which makes it very easy to locate elements within the array. However, when you need a list of any kind, a linked list data structure with references and nodes is the best way to go. And that's what we're going to describe in the next section. A linked list is a data structure consisting of a group of nodes linked together in a sequence. A node is used to store a piece of information. Each node consists of two parts, the data value and the reference. The data value can be used to store any type of object, strings, integers, whatever you wish. The references serve to link the nodes together to form a list. It's also a very good idea to have additional references at both the head and the tail of the list. This allows for faster and less resource-intensive changes to be made to the list. Think of the linked list as a train, with the nodes serving like the carriages of a train. The data values are thus being stored equivalent to the number of passengers within each carriage. A reference can be seen as one of the hitches which links the carriages together. The head is an external reference to the list, and it always refers to the very first node on that list. This enables easy access to the beginning of the list. And similarly, the tail reference is an external reference to keep track of the final node on the list. Normally, you would add the head and the tail before any other element has been added to the list, but for the purposes of this video, we'll do that a bit later. Okay, so to create the first node, we would write node A equals new node, placing 3 as the data value and null as the reference. Let's give node B a data value of 6 and also with null as its reference. We'll give node C a data value of 2 and a reference of null. And now node D, a data value of 4 and a reference value of null. Great, now let's link up the carriages. In order to do this, you need to change the references of each node from null. This is a pretty simple procedure, but do bear in mind that the node itself must exist if you're going to change the reference of it. Let's set A's reference to connect to node B, B's reference to connect to node C, and C's reference to connect to node D. Right, so now let's create a head reference and link that to the beginning of the list. And also a tail reference to store the position of the final node in our list. So at this point, we have a fully completed list, complete with both head and tail references. Adding a new node to the middle of a linked list is pretty simple. There are, however, a couple of steps that really need to be followed carefully. Firstly, you need to find the node which precedes the place where the new node is going to go and set up a reference to it. The next step is to create the new node, in this case node E, and set it to reference node C. So when that's complete, you can use this piece of code, prev.setNext as E, to safely link up the list with the new node added in the middle of it. At this point, it's worth mentioning a common mistake that people often make when adding a node anywhere to a linked list. Say, for example, you have found the previous node, in this case node B. You then create the new node, node E, having null as its reference. If you were to set the reference of the previous node to link with E before changing E's reference, you would lose all of the nodes that followed B. Adding a new node to the beginning of a list is again relatively simple. There's no need to traverse the entire list. You simply need to create a new node and connect it to the head. In this example, node F has a data value of 2 and refers to the same node that the head references. Because you want the new node that has been created to sit at the beginning of the list, you will need to update the head reference. This is done by simply reassigning the head to refer to this new node F. Adding a new node to the end of a list works in a very similar way as adding a new node to the beginning of the list. You start by creating a new node, in this example node G. It has a data value of 3 and a reference value of null. The next step is to set the last node in the list to reference this new node, in this case node G. The final thing to do is to change the reference of the tail so that it references this new node, G. This is done by changing the value of the tail to be equal to the next node up from where the current position of the tail is. Tail equals tail.getNext. Removing the first node from a list is not difficult. All you need to do is update the head reference to reference the second node in the list. A circular linked list is a way to implement a list that has some advantages over the standard approach. A singly linked list can only be traversed in one direction. However, a list that when traversed cannot go further than the final element in that list is not particularly useful. A circular linked list can loop back from the final node in the list right back to the beginning. And here's how we create one. In the standard approach, the final element in the list references null. A circular linked list is set up such that the final element in that list should reference the first element in the list. As the list is now circular, both the head and the tail references can be replaced by one single reference called list. Doubly linked lists are similar to singly linked lists, with one big exception. As the name suggests, the nodes are now doubly linked, and each node now stores 2 references instead of 1. Like a singly linked list, there is a reference which links to the next node in the list, and in addition to this, there is a second reference that links to the previous node in the list. The big advantage of using doubly linked list is the ability to traverse the list in two directions. Unlike a singly linked list, you can go back through the list as well as forwards. This allows for a much more straightforward process when it comes to updating the list. Say we wish to add a new node to the list. We begin by creating a new node, node E. We then set the new node's next reference to point to C, and its previous reference to point to C's previous. The final crucial step is to change the references of B and C to link to the new node. B's next reference will be altered to point to E, and C's previous reference will also need to be updated to connect with E.